Have you ever felt a sudden jolt, a tiny spark, when you reach out to touch a doorknob? That quick zap might seem like a small annoyance, but it's actually a fascinating glimpse into one of nature's most powerful and ever-present forces. Or maybe you've noticed your hair standing on end after you pull off a wool hat on a dry day. These everyday moments are all thanks to the electric force, a mysterious and invisible power that's constantly at work, shaping the world around us in ways we often don't even realize. The electric force is like an invisible web, stretching between objects and particles, creating fields that can push or pull without ever needing to touch. It's the reason why some things stick together, while others are pushed apart. At the heart of this force are tiny particles called charges, protons and electrons, found in every atom. Protons carry a positive charge, electrons a negative one, and their interactions are the foundation of all matter. The rule is simple but profound, like charges repel each other while opposites attract. This principle is what keeps atoms together, forms molecules, and even stops your hand from passing through solid objects, like a table. In fact, the electric force is far stronger than gravity at the scale of atoms and molecules. It binds the very building blocks of matter, holds together the molecules in your body, empowers the flow of electricity in the devices you use every day. When you rub a balloon on your hair and stick it to a wall, you're witnessing this force in action. The balloon steals some of your hair's negative charges and then clings to the wall's positive ones, defying gravity for a moment. On a much grander scale, the same force is behind the crackling energy of a lightning bolt as billions of charges leap through the air in a spectacular display of nature's power. So, the next time you see a static electricity trick or feel a spark, remember, you're experiencing one of the universe's most fundamental and essential forces right at your fingertips. The electric force is everywhere, shaping our world in ways both big and small, from the tiniest particles to the most dramatic storms, and even in the simple moments of our daily lives. How do charges know to attract or repel each other, even across empty space? It's a question that puzzled scientists for centuries. If you hold two magnets close, you can feel the force between them, but there's nothing visible connecting them. So, what's really happening in that invisible gap? The answer is both surprising and elegant. They're constantly exchanging invisible messengers called virtual photons. These are not ordinary particles of light, but fleeting, undetectable packets of energy that exist only for a split second, just long enough to transfer force. Imagine two friends on skateboards tossing a ball back and forth. Each time one throws the ball, the force pushes them apart. This is just like two like-charged particles repelling each other by exchanging virtual photons. The act of tossing the ball is what creates the push. For attraction, picture a boomerang curving back, pulling the friends together. This is a playful analogy for how opposite charges attract. Virtual photons can also create a pull, drawing particles closer, just as the boomerang returns to its thrower. These virtual photons are the true carriers of the electric force, zipping between particles in a never-ending quantum game of catch. They're exchanged at unimaginable speeds, making the forces we feel seem instantaneous. This remarkable idea comes from quantum electrodynamics, or QED, which is our most precise and successful theory for how light and matter interact. QED describes a world where particles and forces are deeply intertwined, and every interaction is mediated by these virtual messengers. In this view, empty space isn't empty at all. It's alive with virtual particles, constantly popping in and out of existence, mediating the fundamental forces of nature. The vacuum is a seething sea of activity, even when nothing seems to be happening. The push and pull you feel between charges or magnets is really a frantic, invisible exchange of energy at the quantum level. Every spark, every magnetic nudge, is a sign of this hidden dance. So, every electric force you experience is the result of this ceaseless, invisible exchange of virtual photons. It's a process happening all around us, all the time, even though we can't see it. The universe is a quantum playground, with virtual photons as the tireless messengers of every electric interaction, weaving together the fabric of reality in ways both mysterious and beautiful. Tracking every virtual photon is impossible, so scientists use the concept of the electric field, an invisible map of force around every charge. Picture a positive charge radiating lines outward like sunbeams. A negative charge draws lines inward, like water down a drain. Place another charge nearby, and it feels a push or pull along these lines. Imagine positive charges painting space red, negatives blue. Like colors repel, opposites attract. Electric fields aren't just a visualization, they're real, carrying energy, and taking time to change. Move a charge, and a ripple in its field travels outward at light speed. This ripple carries information and energy, connecting charges across space. The field concept is key to understanding not just electricity, but also magnetism. Electric fields are the foundation for the forces that shape our universe. For centuries, electricity and magnetism seemed like two completely separate forces. On one hand, you had static shocks, those little zaps you feel after walking on a carpet, while on the other, you had compasses pointing north and mysterious rocks that could attract metal. People thought these phenomena had nothing to do with each other, existing in their own worlds. But as scientists experimented, they made a groundbreaking discovery. Moving electric charges actually create magnetic fields. This realization was the first clue that electricity and magnetism are deeply connected. For example, if you run an electric current through a simple wire, a nearby compass needle will suddenly twitch and move, revealing the presence of a magnetic field that wasn't there before. Take it a step further. Wrap that wire around an iron nail and connect it to a battery, and you've just created an electromagnet, a magnet you can turn on and off with electricity. This is the same principle behind electric motors and generators. So, magnetism isn't just a property of special rocks or permanent magnets, it's actually born from the movement of electric charges, whether in wires, coils, or even inside atoms. Here's something fascinating. A stationary electric charge only creates an electric field around it, influencing other charges nearby. But set that charge in motion, and suddenly it generates a magnetic field as well. The simple act of movement changes the nature of the force it produces. What's even more mind-bending is that whether you see a magnetic field or not depends on your point of view. If you're moving alongside the charge, you might only see an electric field. But if you're standing still, you'll see both electric and magnetic fields. Motion changes everything. For one observer, a charge might appear completely still, creating only an electric field. For another observer, that same charge is moving and suddenly, it's magnetic too. This strange relativity puzzled scientists for years and hinted at a much deeper connection between electricity, magnetism, and the very nature of motion itself. Eventually, they realized that these forces aren't separate at all. They're two sides of the same coin, unified in the laws of physics. In the end, it's motion that links electricity and magnetism, revealing a hidden unity in the universe that continues to inspire scientific discovery today. Albert Einstein's special relativity solved the magnetism mystery. His theory showed that moving objects appear shorter, length contraction, which becomes important at high speeds. In a wire, positive charges are fixed, electrons flow. To a stationary observer, the wire is neutral. But if you move alongside the electrons, the positive charges seem squished together, more densely packed, breaking the balance. Now, the wire appears charged, and you feel an electric force. What's called a magnetic force, in one frame, is just an electric force, in another. Magnetism isn't a separate force. It's electricity seen from a moving perspective. The electric and magnetic forces are united by the laws of relativity. What you call magnetism is just electricity, transformed by motion. This insight revealed the true unity of these forces. Before Einstein, James Clerk Maxwell unified electricity and magnetism with 4 elegant equations. The first, electric charges create electric fields, positive or negative, they shape the space around them. The more charge, the stronger the field. The second, there are no magnetic monopoles, no isolated north or south poles. Cut a magnet in half, and you get 2 smaller magnets, each with both poles. Magnetic field lines always form closed loops, unlike electric field lines, which start and end on charges. This difference is fundamental. Electricity can exist as single charges, magnetism cannot. These 2 rules set the stage for understanding the forces that shape our world. Maxwell's last 2 equations reveal the dynamic dance between electricity and magnetism. The third, a changing magnetic field creates an electric field. This is induction, the principle behind electric generators. Spin a magnet inside a coil, and you generate electricity. The fourth, a changing electric field or a current, creates a magnetic field, even in empty space. This mutual creation means electricity and magnetism are locked in an endless cycle. Wiggle an electron, and you launch a self-sustaining wave of electric and magnetic fields, an electromagnetic wave. Light, radio, X-rays, all are forms of this phenomenon. Maxwell's equations unlock the secret of light and the unity of these forces. The universe is filled with this electromagnetic dance, powering everything from light bulbs to galaxies. Let's see electromagnetism in action with a simple experiment. Drop a magnet through a copper pipe and it falls slowly, as if gravity has weakened. Here's why. As the magnet falls, its changing magnetic field induces swirling electric currents, eddy currents, in the pipe. These currents create their own magnetic field, which opposes the magnet's motion, slowing it down. This is Lenz's law in action. The induced field always resists the change that created it. The magnet's motion is converted into electrical energy in the pipe, which then pushes back. No magic, just Maxwell's equations at work. You're watching energy transform motion becomes electricity, which becomes a force. This experiment is a perfect demonstration of the unity of motion, magnetism, and electricity. The invisible laws of electromagnetism are on full display. From static sparks to falling magnets, we've seen the electric force at work. We learned that electricity and magnetism are two faces of the same unified field, revealed by Einstein and described by Maxwell. Electric charges create fields, magnetic fields form loops, and changing one creates the other. This cycle lets light and energy travel across the universe, connecting everything. The slow-falling magnet shows this unity in action, motion, magnetism, and electricity, all linked. The forces that power our world and light the cosmos are all expressions of the electromagnetic field. Understanding this unity is one of science's greatest achievements. The universe is simpler, more elegant, and more connected than we ever imagined.